Next up is Mikael Widerkrantz from Tillitis, and he's going to talk about a lot of cool stuff. Please take a seat, and let's all welcome Mikael.
Hello, I'm MC. I'm here to talk about a new security device. I'm a member of technical staff at Tillitis. I'm doing applied research and programming on all software parts, as well as helping defining the hardware-software interface. This photo is of me hugging a nice VT100 terminal. Oh, here it is, right? So, Tillitis is a sister company of Mullvad VPN. Mullvad had a small team called the Trustworthy Computing Research that was recently split into two companies. Tillitis is sort of the hardware department. We have built a computer, almost from scratch. It's a rather small computer, but it has some nice features. We call it the Tillitis TKey. The TKey has a unique device secret, UDS, in hardware. It runs small programs. It uses measured boot to create unique identities for all started programs. These programs then talk to your computer or mobile phone, what we call the client. Everything, including the hardware, is released under open licenses. What can you use the TKey for? You can use it for authentication, identification, HSM-like applications like generating certificates, generate secure and maybe signed random numbers, encryption, and many other things. It's a general computer, so you can do anything with it. But what's the point of using the TKey? You can use it for many things. Since the function is defined by the uploaded program, the client computer decides the function of the TKey. So there is no need for new hardware for new functions, since you can upload new programs. Organizations can customize the TKey since they can write new programs or ask someone else to write new programs for it. There is no risk of persistent threats, since nothing is stored on the device. And the hardware gives some nice security guarantees. How do you use it? You insert it into your computer or mobile phone, the client. The client then uploads a small program to the TKey. The TKey receives the program, measures it, and derives a new unique identity for this combination, which we call the Compound Device Identifier, or CDI. Then the firmware switches to a special app mode and starts the TKey program. The TKey program can now see the CDI, but can't see any sensitive data, including the TKey's own hardware secret, the unique device secret. And now a program on your client can talk to the TKey program, and together they do what they want to do. Some advantages of using a measured boot and a compound identity are the CDI can be used as a private key in a public-private encryption system. These private keys are not stored on the device, so there is an unlimited number of key pairs since they are created every time. The private keys never leaves the device either. And the private keys don't leak between programs since they disappear when you pull the TKey out. How is this compound device identity created? Each TKey has a unique device secret, UDS, in hardware. The user can, but doesn't have to, provide a user-supplied secret, the USS, when loading the program. Note that this is not a password or a passphrase or a PIN, since there is no correct answer. This is just additional data to create the new identity. The entire TKey program is hashed, and the digest is mixed with others in another hash function, like you can see here. It's a Blake 2S. This is what the TKey PCB looks like. On the left, you have a USB Type-C for connecting to the client. There's a small microcontroller that speaks USB. It's a USB-C DC, so for the client, it looks like a serial port. There's a flash chip that is used during hardware and firmware development. In the end-user version, we keep our hardware design locked down inside the next part. And the next part is where the real magic happens. The large chip on the right is an FPGA. And many of you probably know what an FPGA is, but I can explain it to the rest of you. An FPGA is a kind of chip that can be customized into other chips. So our hardware design is inside this chip and makes it into our own hardware. So what's in the FPGA? This is a block diagram of the FPGA in our hardware design. I'm not going into detail here, but let me tell you about some of these blocks. There's a CPU, of course, some firmware in RAM, a special firmware RAM, and the unique device secret. There's also a simple timer, a host interface, a touchpad controller to, for instance, assert presence when signing something. There's also a source of true randomness, some RAM to run the programs in, and some LED controls and things like that. Some specs. The CPU is a 32-bit RISC-V. We use Clairvolt's PicoRV32 with multiplication, but without division. It runs at 18 megahertz. We have 128 kilobytes of RAM for the TKey programs to run in, and currently our biggest program is about 27 kilobytes of text. All the hardware cores I just talked about are memory maps, so they can be reached by the CPU. We recently added an execution monitor, so we can mark parts of the memory, like the stack, as non-executable. We also added hardware-assisted ASLR and RAM scrambling. There's support for our architecture in LLVM from version 15. It's the thing about without division that's needed. But if you're really careful, you can use earlier version of LLVM as well. The software we have written are an emulator, which is a fork of QEMU, the firmware, which is also the bootloader, as I explained earlier, some client programs running on your computer or mobile phone, and some TKey programs. Having an emulator means you can try things out right now, even if you don't yet have an actual TKey hardware. Our client programs are all written in Go. There's TKey RunApp, which is basically a dev tool to upload and start any TKey program. TKey Sign signs files, and an SSH agent. Our SSH agent is compatible with OpenSSH. It's written in Go and runs on your client. It runs the TKey program Signer, and is currently packaged for Ubuntu, Debian, Homebrew for macOS, and Windows support is coming along. You can use the agent like an ordinary SSH agent and log into other computers, sign Git commits, and do other SSH operations. So far, our software development kit on the client is mainly 2 Go modules. TKey1 is a module to detect and talk to a TKey and load a program. And TKey1 Sign is a module to communicate with the TKey program Signer. Let me show you the first TKey program. This is the first ever program that ran on real hardware. It's a small assembler program I wrote. It just blinks the LED, but when it blinked, I was pretty happy. That was a good day at work. Here are some slightly more useful TKey programs. More are in development, but we are focused right now on getting the actual device finished. Signer signs messages sent to it by the client using the compound device identifier as a private key and to derive a key pair. It uses elliptic curve for signing operations. It's written in C and uses the monocipher library for crypto operations. RNG stream outputs really good random numbers. It's also written in C. It uses the true RNG to seed a pseudo RNG again and again. The TKey software development kit is based on compilers in the LLVM framework. We have so far used C, but it should be entirely possible to use Rust or SIG instead if you are willing to do the work to do the bring up. So far, we provide a small C runtime, a small libc-like library, and we have ported the monocipher library for crypto operations, as I mentioned. We provide a header file for addresses and constants because all our hardware cores are memory mapped. There are no external dependencies, no operating system, everything is bare metal. However, the firmware also exports a single C function for use by TKey programs. It's Blake2S. It's a hash function, so the TKey programs themselves don't have to implement a hash function like that. They can use the firmwares. It's not a real system call because there's no context switch and no change of the hardware mode. You can verify that the TKey you received has the same identity and firmware as the one we sent out. You get the TKey through the mail, and perhaps someone nicked your mail and replaced it with something else you want to check. Our verification is done by us running a program on all devices before delivery. We sign this program's public key and the firmware hash it computes. We publish these signatures on the web, and we provide the client programs that runs the same TKey program, checks the identity, the firmware, and verifies our signatures. In summary, we have created a new RISC-V computer in a USB stick form factor without persistent storage, which uses measured boot to create unique program identities with many uses. We have developed some useful programs and libraries for both the client and the TKey and released everything under open licenses. If you want to know more, please visit our website at tillitis.se, where links to our repos and other information is available. We hang out on RC, like old-timers, and a bridged matrix room. Thank you.
Thank you very much, MC. Any questions?
When can I buy one?
Probably later this month, if you're willing to buy a dev kit, probably.
Yeah, I just had the same question, so.
So, if I understand it correctly, there is no secure element in this device.
That's true.
So all of the secrets are sort of derived from this UDS.
Yes.
But it itself isn't protected in any way, or.
Well, the UDS in the hardware is not available for the TKey programs. When we switch to app mode, we switch a circuit inside the hardware design, and the UDS is no longer memory mapped. And the UDS itself, during development, we used a flash chip to keep the FPGA bit stream in, but in an end-user environment, we lock this down in the NVCM memory inside the FPGA. We use a nice 40, and it has some configuration memory inside it. And then we blow a fuse, so it's not possible to read out the NVCM and the bit stream, including the UDS, from the FPGA. If you have endless time and a really, really good microscope and some really good expertise, you could probably read out the UDS anyway, but that's out of scope.
Okay, so you basically say that it's difficult enough to extract the UDS.
Yeah. And it's the same thing with the security element. If it has some sort of ultra secret inside the hardware, that should also be really tough to get out, but it might be possible for someone with endless amount of time and resources and electron microscopes.
Yeah, sure. Okay, thanks.
I have a question for you. When you're doing the firmware update.
No.
What? No?
No firmware updates.
So do you assume all programmers are error-free?
Well, nothing is perfect, and
Okay. Thank you.
the firmware is really small. It's about 4K, and it's probably we are probably able to audit it well enough to keep it without major bugs, I hope. And if you want to, so everything is part of the bit stream. So if you buy a dev kit with an empty TKey and the Flash program that goes with it, you can update the firmware. But in an end-user version that is locked down and blown fuses, all that, no firmware updates. But very little of the function depends on the firmware, because you upload program to the TKey and run those programs when you use it, and that's the basic functionality is given by the programs you run on it, not by the firmware.
I have another question. How would you compare this device to, well, possible alternatives in the market? I don't know about possible alternatives in the market. I'm just guessing, but you should have done some sort of market research here. And are there similar experiments and projects elsewhere? For instance, what about the YubiKey HSM thingy? How would you compare this to that?
I can't go into detail about the YubiKey HSM, but other things like the YubiKey you use for authentication has a limited number of functions, and they are defined by the firmware on the YubiKey. So it's not possible to run any kind of programs on the YubiKey, like on the TKey.
You cannot run your own programs. You can only run what's there.
Yeah, exactly.
Anything else somewhere?
Well, some of these ideas are not new. Some of these ideas about the compound device identifier and measured boot and using a measured boot as a way to get an identity is something that Microsoft researched, found out many years ago, and in the DICE project. So they had this idea about using it for Internet of Things stuff. So, but I haven't heard about any other hardware product you can buy or soon buy.
So the UDS key, is that selected by you?
Yes.
So you know the UDS key?
Yes.
So if I don't trust Tillitis,
Yeah.
can I buy the dev kit and select my own and then
Yes.
make it as secure? So I can blow those fuses as well?
Yes.
Okay, that's my question.
Great. No one else?
Thank you.
Thank you.